Hey guys, welcome. I think this is the seventh time of me recording this video because there are so many words. You have no idea. It's yeah. So let me try that once again. Last two videos we were covering frequency dependent analysis, and this being a part of dynamic analysis. We covered direct formulation. We covered modal formulation. Now it's time to step into the domain of transient dynamic analysis. This time around, it's time dependent, not frequency dependent. I think I've nailed it this time. So let's jump into it. So yeah, just that you know which tutorial I'm following here. It's the tutorial 1310, direct transient dynamic analysis of a bracket. And so you see we stepped a bit up our game from a plate to a bracket this time. And this is the model. So first things first. I have found there to be an, I would say, modeling error or version error. I don't know really how to tell you that, but if you would follow the tutorial step by step with the model files which you can currently get, speaking of December 2022, there is something not quite right here. To be fair, I did not check if it's working differently in Hypermesh because it is a Hypermesh and not a Hyperworks tutorial. But I think it's just an error, and I also will contact Altair about it, and they will probably resolve it. So what did I find? What did I find here? So two things. First thing, there will be a problem later on when you have this set of nodes. No, it's not those. No, it's rather this node here, and this node is included in a set called center, and the center has no card image. No card image, which in that case will you require to assign one, and by doing that you will lose the connection to the node, so you will have to just yeah, do it once again. So this is the first thing. This set should have a set card image. All right. Second thing, which is a little bit more disturbing to me, is the system or solver mass. So I think, and here I have to call out on the more experienced folks, there should be a solver mass option in previous release of Hypermesh, I think. So there you could just go right click, create solver mass, or I think system whatever and then solver mass. It's not there. It is not there. I found a way to create solver masses, but unfortunately it's just with TCL commands, and I found that a little bit tricky. So I went on and googled a lot about this, and yeah, so as it seems, the solver mass in here, which should have a mass here, you can also see that it is here because see the entity selector is set to solver masses, and if I can select this, but now comes the point, there's no mass. I don't really get it. If I just write that as a solver DAG out and import that in Hypermesh, there's no mass at all. You cannot find a mass. Or I'm stupid about that. Could be. Could be. But yeah, so what I found to be the solving way for this issue, just get rid of the solver mass entirely. And then you can just create a mass going, I think it's in the model ribbon, then to masses. And here you just enter conm2 is the right element type because it does not require you to have a property setup, which we don't want to do. And you just select the node in here and enter no property, enter a mass value of 1000. And I found that value, I think, in the model. It was a wild ride, to be fair. So in the model, I could spot there, I think it was here, I could spot a conm2. Yeah, if you zoom here really into the screenshot, you see that conm2. So this is what gave me the hint. And also there's somewhere I found that it is 1,000 units, whatever the units is here. I'm not sure about that, but yeah. So just that you know, those two things you should check first, or yeah. Hopefully, Altair will resolve that, and the binary file, the HM file you can download here, will have that already solved when you watch that video. But create a mass here, you will see this entity here, and then it's also set under the element, so you see that column too. And now you're ready to go. So quick to sum up, two things: set card for the center set, and also the mass is to be defined as 1,000 on this center node. All right, now we can start. So first of all, what are we doing here? We are interested in the time-dependent response of a structure onto a time-dependent loading. Okay? So first thing what we want to do is we want to create a curve for this loading, because it's time-dependent, so it will change. It will change with a different kind of step. You can see that here. This is our curve which we want to define. You start at 0, you go to 0.1, and this is the stepping up of the force. Here the force is acting, and you on the x-axis you can see it's just the time. Now this is fairly easy. Right click, create and curve. So we can do that. It's always a little bit big on the screen here, so I have to shrink that down and give the editor some space here. Now I will call that table D1, because that will be the card image. And here I have to tap. I will get an error. I will have to tap here. Meh. Not sure how this is done. Oh. No, okay. All right, 0, 0, 0.1, 0. No, 0, 0.15, 1, and 5. You can shift tab backwards, that's great. 5, 1. So this is the curve, right? 0, 0, 1, and here's the step. That should be it. Now, if I do that like this, bear in mind that this will not be a table D1 card, or table D1 curve. Yeah, that's just a thing you have to keep in mind, because you can see it now here in the curves. You just have table DMP1, and this is just wrong for our case here. So change that to table D, or tab, no, table D1, and you're good to go. Keep that to linear, that's all good. Now we have that. Next thing we want to do is create a t-step load collector. The t-step load collector is used to just do our time stepping. So we call that t-step. We will put a t-step card image to it. And then we have to set more or less 2 values. We can set 4, but n is the number of steps we want to have. And you see here the step numbers. The first one, which is good because we just have 1 step, so that's perfectly fine. So we set 800 for the number of steps, and the time increment would be 0.0055. And now the tutorial also tells you that you should set that to 1, but it's also the default value. What this is doing is it sets the number of steps to skip for output writing. So 1 should be every output is saved. So yeah, we want to have everything here. And in this case, 800 times 0.005 gives you 4 seconds of time, and you have 800 data points in there. So this will basically create the response curve, or the precision, you could say, of the response curve. If the time step is too large, you will not capture the real behavior of the system well enough that you can derive the responses from it. So keep that in mind. It's important to set that to a decently small value, but not too small, because then you will run out of time. So it's always a balance thing, like so many times in life. All right, let's go into the next steps. Next, we want to create a load collector, which is used then to excite our loading. And this is usually has no card image. I'm always getting that wrong. But it's called the area, and this is because of the type of constraints we will be using, which are of type the area. So we created a load collector, and if you just double click on the load collector's browser, you can see then that you see that the area is the bold marked component, which is the current component. So everything I'm doing now goes into exactly that component, and that's exactly what I want. So I created this, and then I want to create my boundary conditions. Now you will find that in Analyze, and then on BCs, then on Constraints, and then you're in the panel. I will move myself up a little that you can see what I'm doing here. So, it's a bit different than last time. We don't want to pick a single node or pick any nodes to be particular, but we want to pick nodes in a set. And first of all, that I don't forget it, change the load type to the area, because we don't want to do SPCs. Next up is I want to just unselect everything but the DOF3, because this is the DOF, which is translational Z direction, in which our force should act. And the amount of force in this case is 1500. I don't know about the units, to be fair, because yeah. But I think that could be newtons. That would be 150 kilos. Yeah, I don't know, maybe. Now, this is all set. Now the selection of the nodes. You can click here on the yellow selector and then by sets. Then you can check the force, and always this is what gets so many people. If you just happen to select both and you want to unselect, why the hell does it not unselect? You have to right click. Yeah. So force is the right one here. So click on select here, and now you see the nodes are selected. Now click on create, and you can see that you have the boundary conditions set. If you want to be even more sure about it, you can just change the visibility, and you can see those little signs of the boundary conditions. Okay, let's change that back. We are done here. Now we should now create the T-load load collector. Oh, it's not a load collector, it's a load step input. It's a different thing. So this, we created the load collector, the area. There were the boundary conditions. And now we want to have the T-load load step input, which connects our curve with the load collector, which is then excited with that curve. Excited is not really the right word here, because, yeah, you know where I'm coming from. I'm coming from the frequency dependent analysis I did last. So, yeah, it's not exciting. I will stop now. All right, so create a load step inputs collector. Yeah, change that to time dependent load. So dynamic load time dependent. So which one load collector I want to excite? Yeah, I can use excite. It's okay. It's the area. And the table I want to use is the table E1. Now, it says that it uses load automatically, but I will just make sure and set it that this is the case here. I think that's it. So we made that connection, and we can go on to the load step definition, which is rather straightforward. So you create a load step, and this load step should be of type transient, and in this case direct. And you want to have the SPC collector for sure. And by the way, the SPC collector we did not fill with any constraints, but they are just here. You see those little green signs here? Those are boundary conditions fixing this bracket in place. Okay, dynamic load, we have that too. This should be the load step input 1. Oh, bad name. I should have named that our load, but you know what it is, hopefully. We have no frequency here, but we have a T-step. Oh, and I made a mistake here. It's a T-step time. Be sure to check that as T-step time, because it's time dependent. And so you would want to have it here. I'm not really sure if it would break things if you had assigned it to just t-step, but I think it would. Maybe you can try. Okay, so this is assigned. I think that's about it. So we have t-step, we have the deload, and we have the SPC. We don't need anything more. Now let's go to the damping parameters, and this is where it gets a little bit complicated, from my understanding. Damping parameters, we set that also for the frequency-dependent analysis. I think for the modal and also for the direct approach. So bear with me a moment. So we go into the control cards, and the first thing we do is we go to the parameters, so param. And here we just check G, which is the structural damping, and I just love those kind of menus, like everybody. And we will use 0.2. I think that's a similar value we had in the last model as well. But now comes the trick. We also check V3. And you might wonder what this is. And so did I. And I will tell you in a minute. So 300 is the right value according to the tutorial. And in the tutorial it says this parameter is used in transient analysis to convert structural damping to equivalent viscous damping. And first of all, I was, what? Viscous damping? Fluids? What? No. The thing is, I then researched a little bit, and I found that again. I mean, I just Googled it, and that was one of the first pages, and I thought that to be quite interesting here. So you see that here. Because transient response analysis does not allow for complex stiffness. Remember, we are solving complex algebra to get our response. And we have no transient stiffness. Or transient complex stiffness we could compute for in a complex space. Structural damping must be converted to viscous damping. All right, makes sense. And I was just glancing, I did not read it line by line, but I was just glancing through here. And one thing what struck my mind was where G is a structural damping coefficient, right? Yeah. But here, you see that equation. You see m times the acceleration plus whatever. Here's the structural damping, by the way, times the stiffness times the displacement of dependent on t. You see that this is not, it's not related to the velocity, to u dot, right? And I think that is the case because that's why the structural damping coefficient G is not enough to use that here, because you want to have this B. And this B here is the viscous damping, right? I think so, because it's said here, right? Yeah, so in this case you can see that the W3 is set here. Yeah, and you can make that up a little bit for your own if you want. I will not go into that much of a detail here, but yeah, so you just understand that. And that's special for the direct. You will see in the next video that the modal approach does not require you to do viscous damping here. But yeah, so that you know. Okay, so we set those two values. So parameters are set. Now we come to our favorite card, which is global output requests. Why favorite? Because it had a happy time to just punch us into the face when we wanted to set the displacement set. But not this time. Not this time. Because we want to both, we have formed both. This time we will have, we prepared. Prepared. Sorry about that. So option is set ID. And now I hope, but I'm pretty sure that this will work. So I click double here. And now I move myself all the way. Center. And there's a 1. Yes. Okay, so this is set. I think that's all what we need here, right? So both for form and the set ID is also done. That's good. See, that was fast. Now let's go to output. This is the last card we want to use, and we want to specify 2 outputs. And the first output should be HG trans, which is transient hypergraph output, and we want all, and we want to have H3D and also all. That's about it. Now we can run the job. I will just save that as a database. Save as hypermesh model, and I will just use a different name that I have no conflict with my initial file and my solving file. So save that here. And now we can run it. And just to be even more, that is even faster to open, that I have opened already a Hyperview instance with the results. But I will show you that I'm not cheating here. I will open the session and I will open the one we solved right now, which is the one with the 2, which you can see here. Yeah, but you see, yeah, the tutorial requires us to do a little bit of post-processing here, which we will do, because, yeah, so we go into the rainbow color bar here, or circle, and just put the X and Y trans curves to off. So this off, this off. And then there should be a, yeah, we can just fit our curve here, and this is more or less the output we have in our tutorial as well. Yeah, so I think that's about it. Now what you can see here is, maybe I should have talked about that a little bit in the beginning. So we had a mass here, right, of 1,000 units. And then we had a force acting in minus z direction, which was at 0 for a certain time, and then dropped or raised to 1,500 units. So you push down here, and then this mass will just swing. And this is this swing action. This is shown here, and you can see how the damping is acting here, and just, yeah, within 4 seconds or so, this will come to a rather converged state. Another output you could get too is, and this is not part of the tutorial, but I will just open it here, is you can get the transient analysis output and see it in Hyperview as well, and animate it, and for sure we'll do that here for a second. So this is the typical, here, this is the typical output you get when you press on results. This is Hyperview, this is all set here, and you can, for example, go just to the displacement and just animate it. And you can see, well, it's a little bit tiny here, but we can fix that. We can just go into the deformed shape option and just press 100. Yeah, you can see that little thing bouncing around here. So this would be the transient solution. That's quite nice. I like that. This is structural engineers' joy when when you get this kind of results and see how the structure behaves, and it kind of makes sense, and you see, oh yeah, could be. Yeah. All right, yeah, I think that's about it for this video. Next up, we will look at the modal approach, which is kind of, yeah, it's solving the similar problem, but with a different approach, and it has some advantages, some disadvantages compared to this method. And yeah, it's just good, just my own opinion, just good to have both ways and, yeah, ready, so that you can act in both directions. And if you need the one, you choose the one, and if you need the other, you choose the other. And yeah, that's just making you a better engineer in the long term. So I would suggest that you learn both ways, and yeah, happy to exercise a little bit within each domain and get an understanding also for the fundamentals which are included in here. All right. Yeah, thanks again for being here, for watching this video. I had a fun time doing this, and yeah, glad to see you in the next episode. If you liked that video, please like, subscribe, tell me what you liked about it. Tell me what your experiences are with that kind of simulations, or what you wanted to see additionally to this kind of analyze. Then yeah, just leave a comment or write me a mail. All right, bye guys.